Let's take a look at another example of density. This time we'll look at a variable density example. The last one we did, as crazy as the calculations were, it was a constant density. Our rho of xy was just 1. In this case, we got a variable density example. So we're going to find the center of mass on the upper half of the disk that's bounded by a circle with a radius of 2 and a density of 1 plus y over 2. Now, because the circle is a base, it might be easier to convert this into polar coordinates rather than having to deal with a base that's got an equation of x squared plus y squared equals 4. Now, when you do that double integral to find mass, you'll still do a rho of xy, except now your dA is actually your r dr d theta, because that's what the calculation is in polar form. So that dA turns into your r dr d theta. So in polar form, you've got your rho of r theta, right? Not xy, r theta, r dr d theta. So this is the double integral that we need to set up. All right, well, the first thing is, what does the base look like? The base is the upper half of that disk. So it's just the top half of a circle with a radius of 2, which means that the equation of that circle is r equals 2 on the theta interval from 0 to pi, right? It doesn't go from 0 to 2 pi. It goes from 0 to pi, and certainly that'll have an impact on our limits of integration. All right, so same process as before, except in polar form. First thing is, let's calculate the mass. So the mass, we said, was the double integral rho of r theta, and then instead of the dA, we'll have an r dr d theta. Well, we were given a rho in terms of y. How do we get a rho in terms of theta? Well, remember that the conversion is x equals r cosine theta, y equals r times the sine of theta. And so we'll take that 1 plus y over 2, and we'll turn it into 1 plus r sine theta over 2. And so now I can set up my double integral of 1 plus r sine theta over 2 times r, right, whole thing times r, dr d theta. We said the radius went from 0 to 2, and because it was only a half circle, the theta values go from 0 to pi. All right, let's multiply. That'll give us an r plus 1/2 r squared sine theta, integrated with respect to r, from 0 to 2. Now, remember, we're integrating with respect to r. That sine is just a constant. So take the antiderivative with respect to r, and you get what? R squared over 2 plus r to the third over 6, because there's a 3 up on the top. There's a 2 that's already there. And the sine of theta was just a constant, so it comes along for the ride. We're going to evaluate at 2 and evaluate at 0. 2 squared is 4. Half of 4 is 2, plus 8 over 6 sine theta. When you evaluate the lower limit of integration, you just get 0. So I suppose I could simplify that 8/6. Let's do it when we write out the next integral. So the next integral then will be just the integral from 0 to pi of 2 plus 4/3 sine theta integrated with respect to theta. So when I integrate with respect to theta, I get 2 theta. The antiderivative of sine is negative cosine, so minus 4/3 cosine theta, evaluate at pi and at 0. All right, so that gives me 2 pi. The cosine of pi is negative 1. Minus a negative 1 gives me a plus, so I get plus 4/3. Now, when you do the 0 part of it, yeah, you're going to get a 0 for the theta part, but you're going to get a minus cosine of 0. Cosine of 0 is 1, so you'll get a minus 4/3, which gives me 2 pi. I got a 4/3 here, I got a 4/3 here, so plus 8/3. What is this? This is my mass. When you go back to that original region that we were looking at, the original region was symmetric to the y-axis. Right, it's that half disk that's up on the top. So that must mean that the mean for the x's is just 0, right? Because it's sitting right in the center, it's symmetric across the y-axis. So that saves us a little bit of work, in that we only have to find the center of mass for the y-coordinate. All right, let's try that. The center of mass for the y-coordinate is going to be 1 over the mass times the double integral of y times rho of r theta. Don't forget the r, dr, d theta. Right, what do we do with this? First of all, that y, we said, can be represented as r sine theta. And that rho, we already had as 1 plus 1/2 r sine theta. Ooh, this is going to be fun. Let's multiply all this out. So I get, let's work just on the inside here for a minute. So I got an r sine theta times 1 plus 1/2 r sine theta times r. I multiply them across. The first term here will give me an r sine theta times r, which is an r squared sine theta. The second term here will give me a 1/2, 1, 2, 3 r's, right? 1, 2, 3 r's, so r to the third. A sine theta times a sine theta is a sine squared theta. So I'm going to integrate that with respect to r. We said our r limits of integration were from 0 to 2. Right? This looks kind of funny because we're integrating all these sine functions with respect to r. All that means is we leave the sine functions alone, right? Sine functions don't come along. They just come along for the ride. They don't make any difference. So I get r to the third over 3 sine theta plus r to the fourth over 8, because I got a 2 already here. 2 times 4 gives me 8 sine squared theta, 2 and 0. So 2 to the third is 8, so I get 8 thirds sine theta plus 2 to the fourth is going to be 16. 16 over 8 is 2. So 2 sine squared theta. If you put a 0 in for r, you don't get anything. So that's the inside limit of integration. Let's do the outside limit of integration. Outside limits of integration are going to go from 0 to pi. Remember we said that that was the half circle. So we're going to integrate from 0 to pi of 8 thirds sine theta plus 2 sine squared theta. Well, we could do some sort of a trig reduction formula to get rid of that sine squared theta, but isn't it true that I can write sine squared theta as 1 minus cosine 2 theta over 2? Yes, that's what I'm going to do. So I'm going to rewrite this as the integral of 8 thirds sine theta plus 1/2 minus 1/2 cosine of 2 theta. But wait, wasn't there a 2 on the outside here? Yeah. So if I multiply both of these by 2, you notice this becomes a 1 over here. And this piece over here, the coefficient disappears. Right? So I took my 1 minus cosine 2 theta over 2. When I multiply it by 2, it just becomes 1 minus cosine 2 theta. And now that's not so bad. All right, so there's a fraction involved. The antiderivative of sine is negative cosine. So negative 8 thirds cosine theta plus theta minus, when you take the antiderivative of the cosine 2 theta, the chain rule kicks in. So you get a sine of 2 theta over 2. All right, we're going to evaluate this at pi. We're going to evaluate this at 0. Cosine of pi is negative 1. Negative 1 times negative 8 thirds is positive 8 thirds. If I substitute a pi in for that theta, I just get pi. What's the sine of 2 theta? The sine of 2 theta is just 0. Okay, so that's the first half. Minus, if I put a 0 in for cosine of 0 is 1. 1 times negative 8 thirds, negative 8 thirds. And that's actually the only constant that matters. The rest of them just come out to be zeros. So when I calculate this, I'll end up with 8/3 plus 8/3, which is 16/3 plus pi. But I'm not quite done yet, because at the very beginning of my formula was that 1 over m. We'll go all the way back up here. And this guy over here, the 2 pi plus 8 over 3, that's my m. So if m is 2 pi plus 8 over 3, then my y center of mass is going to be 16/3 plus pi divided by 2 pi plus 8/3. Oh, let's hit the top and bottom with a 3. All right, so hit top and bottom with a 3 and then distribute. So that'll give me a 16 plus 3 pi on the top, 6 pi plus 8 on the bottom. So what is my center of mass? Well, remember we were kind of saved by the fact that there was some symmetry involved here. So the x-coordinate is just 0, and there's our y-coordinate, 3 pi plus 16 over 6 pi plus 8. No, you don't have to write it in that order, and no, you can't simplify it by breaking it apart across the plus signs. That's my center of mass, and we use polar coordinates because the base was a circle. Seemed like an easier thing to do. All right, let's take a look at one more case, and that is the case of 3 dimensions. If you have 3 dimensions and you want the center of mass, now you've got 3 coordinates in that center of mass. You've got an x, a y, and a z. So now it gets a little bit more complicated because you've got to have the moments in the yz plane, the moments in the xy plane, the moments in the xz plane. When you go to set it up, it's going to look like copy and paste from the previous two. Again, except that you're going to have an x when you go to do the x center. You'll have a y times rho for that, and you'll have a z times rho for that, and everything else remains the same. We're not going to do very many of these either in the homework or on tests or in examples here, but I do want to at least set one up so that you can see what they look like. All right. So I got a center of mass for a solid with a constant density. Solid is bounded by a paraboloid, and the plane z equals 25 up on the top. What would my mass calculations look like? Well, the mass calculations are going to involve a triple integral, because when I go to look at this, where are my z values going to go? If I get one of these shapes like this, they're going to go from x squared plus y squared up to that 25 where the lid is. So my z values are going to go from x squared plus y squared up to 25. Wouldn't it be easier if I did this in polar coordinates? So instead of doing x squared plus y squared, I could think of them as r squares. So maybe they go from r squared up to 25. Well, if I'm looking at r squared equals 25, then really what I have is I have a circle with a radius of 5. So I have r values really that go from 0 to 5. I have z values that go from r squared to 25. And then how about my theta values? Well, there's nothing that says we only want part of this paraboloid, so the theta values will go from 0 to 2 pi. All right, let's throw this in a quick formula for mass calculations. The mass will be the triple integral of r dz dr d theta, where my z's go from r squared to 25, my r's go from 0 to 5, that's the radius of the circle, and the thetas go from 0 to 2 pi. Good. Let's evaluate the first couple of these, right? If I integrate this with respect to z, not with respect to r, respect to z, then I end up with rz evaluated at z equals 25 and at z equals r squared. So that gives me r times 25 minus r times r squared. So I get 25r minus r cubed. All right, now my next step will be to evaluate it from 0 to 5, integrate with respect to r. So integrate from 0 to 5, 25r minus r cubed with respect to r gives me 25r squared over 2 minus r to the 4th over 4, 5 and it 0. When I throw that in, I will get 625 over 4. Then my last step is to integrate that from 0 to 2 pi of 625 over 4 d theta, which will just give me 625 times 2 pi over 4. So 625 pi over 2. All right, that's the mass. Then if you want to find the center, then you've got to throw it back in and do each of those formulas. So this one actually turns out not to be terrible because the x's and the y's are both 0 because there's that symmetry across that axis in the paraboloid. So the x is 0, the y is 0. It turns out it's only the z that matters. And so if the center for the x and the center for the y are both 0 by symmetry, then the center for the z is just going to be 1 over the mass, triple integral of r z dz dr d theta. That z comes from the formula. Remember we said whichever center it was, you're going to end up with an extra variable from that variable? Well, that's where it comes in. All right, so if you want to set limits of integration, you'll end up with z's going from r squared to 25. The r's will still go from 0 to 5, and that will go from 0 to 2 pi for the thetas. And then you can calculate that out, and the center of mass for that will be 0, 0, and that number. But I'm trying to avoid some of these three-dimensional ones because you can see the calculations just get more intense, but the idea behind it is not terrible. All right, that's the end of 16.6.